Hello and welcome back to another IB Math speedrun with me, Vince. So in this final speedrun of this subchapter, we'll be going over the exponential function and Euler's number. So yeah, what is the exponential function? Well, to best understand it, let's look at this case where you have $1 and you're investing it at 100% interest. So if you compounded this, say you've invested it for 1 year and it's compounded annually, you'd get 1 plus 1 times 100, which is equal to $2. But what if you compounded it semi-annually? What if you got 50% interest for each half of the year? So you would get in the end 1 plus 1 times 1.5. Actually, it's just 1 times 1.5 squared, which is equal to 2.25. So, but what if you invested it at 25% for each quarter? Well, then you'd get 1 times 1.25 to the 4, which is equal to 2.44. And we can keep on going. We can keep on investing money at smaller and smaller increments, like compounding it at smaller and smaller increments, and eventually you'll find that it tends to this number 2.718. This is something we call Euler's number, and it's the function for exponential growth, since it means if you have an infinitely small amount of intervals that you compound it at, this is the maximum amount of growth that you are going to get. So now we can talk about exponential functions. And exponential functions are the family of curves of the function just g to the x is equal to a to the power of x, for which a is a positive real number and a is greater than 1. So this means that we have growth over time. And these have some properties. First of all, they have no stationary points. Actually, let's write these out. No stationary points. They are always increasing, which means that they always have a positive gradient. X-axis is a horizontal asymptote. There are no vertical asymptotes. They are all one-to-one, they're all one-to-one, and they all pass through the point 0, 1, but the gradient of the function will increase at this point as the value of a increases. So say let's look at an example function, which is 2 to the x. So if we have 2 to the power of x, it looks like this. As you can see, it passes through the point 0, 1. It has, let's just compare, no stationary points. You can't see any stationary points here. It's always an increasing function. The x-axis is a horizontal asymptote. As you can see, it never touches it. It's a one-to-one function, since we can never draw a horizontal line and intersect the line more than once. Passes through 0, 1. A similar function is 5 to the x, 10 to the x, and of course e to the x, but we'll get to e to the x a bit later. Now, those are exponential growth functions, but we also have exponential decay functions, which is where we still have a to the power of x, but this time a needs to be between 0 and 1. And so this is a bit different, because this means that as x increases, the value of y actually decreases. So we still have no stationary points, but these functions are always decreasing. X-axis is still a horizontal asymptote, no vertical asymptotes, one-to-one, and they always pass through 0, 1 again, but the gradient decreases here as the value of a increases or gets closer to 1, since if we have a lower value of a, this decreases faster. And so finally, we have to look at the function e to the x, which is the exponential, I guess it is an exponential. This is the exponential function. So y is equal to a to the x is an exponential function, but this is called the exponential function. And this is very interesting because it has several important properties. First of all, we can use it to model exponential growth, but the second most, the most important property is that it is invariant under differentiation. What do we mean? We mean that if we differentiate ex, e to the x, it will simply be equal to e to the x again, which is very surprising. So we can prove that you can prove this for yourself, or search it for proof, but this is very important, and we can then use this to solve lots of questions. So let's jump right into solving some actually wait, we have to talk about one more thing first, and it's the inverse of the exponential function. So the inverse of an exponential function is equal to log a to the x, since if f of x is equal to a to the x. So these two are mutual inverses. This means if you have a to the log a to the x, this is simply equal to x again. So the inverse of the exponential function, which is log e to the x, well, we denote this as ln x. This is the natural logarithm function, and we have this special notation because it's very important. So with that being said, I think we can now jump into some questions. So I'll do the odd ones. So the diagram shows some graphs of exponential functions. These two over here. I mean, of course, wait, the x-axis is below this line. On this one, this is the point -1, 4, and on this point we have 2, 4, and we need to find the value of a, because these are all exponential functions of y is equal to a to the x. So in order to find a, let's look at this first one. First, we have 4 is equal to a to the 2. So we simply have a is equal to 2. So this one is y is equal to 2 to the x. For this one over here, we have 4 is equal to a to the -1. So a must be equal to 1/4. So this function is y is equal to 1/4 x. So this one is exponential decay here, and this one's exponential growth. Next, I guess I have to skip to the fourth question. So we need to solve the equation e to the x plus e to the -x is equal to 2, and so we can do this by converting everything into natural logarithms. So we have ln e to the x, which is of course just x. Oh, hold on, wait. No, sorry, the correct way to do it is to multiply everything by e to the x. So we have e to the 2x plus 1 is equal to 2e to the x. So we can factorize this into e to the x minus 1 is equal to 0. So e to the x is equal to 1. So therefore x equals 0. So that would be the answer for this one. Yep. Now next one, we need 3 graphs of geometric transformations. State the transformations, give the new functions in terms of x. So, I mean, you only have to do one of them, which is this. So it's a mirrored version of the graph of e to the x. And so this is quite simple. The transformation is a reflection along the x-axis, since the original function looks like that. And so this new function is simply negative e to the x. Yep. Next, we need to, given that f of x is equal to a to the x, find f of -1 to the x and f of f to the -1 to the x. So f of -1 to the x is simply log a to the x, and so this would be equal to a to the log a to the x. And so, well, the thing is, this is actually equal to x, since if we get the inverse of a function and we compound it with the original function, we should get the number back. So therefore, a times log a to the x is equal to x. So that's something important that you want to know. Next, I'm going to go to question 9. Sorry, I'm jumping around a bit here. So we have on separate axes, which I will just do on Desmos this time. On separate axes, draw the graphs of y is equal to log 2 to the x minus 2. I guess we have to write log x minus 2 over log 2, which is fine. And we also have log x over log 2 minus 2. So geometrical transformations of log y is equal to log x over log 2. So we need to identify the two geometrical transformations that lead to this. So this blue line is the easy one. We just translate it downwards by a factor by 2. But this is a bit harder to see this shift over here between the red line and the green line. And is it a movement right? I think it actually is just a translation to the right. Yeah, it's a translation of the original graph in 2 units to the positive x direction. So let's look at the final question, which is identify the domain, any asymptotes, and axis-intercepts of this function. Y is equal to log 2 to the 4 plus 2x minus 5. So we need to get the domain, any asymptotes, and axis-intercepts. So what we need to know about the log function is that it has a domain where it has to be greater than 0. So, other way around, sorry. It has to be greater than, or equal to 0. There are no like negative log values. You can't have log 2 of negative 1. There's simply no value for that. So let's look. This means that the domain means 4 plus 2x is greater or equal to 0. So 2x is greater or equal to negative 4. So x is greater or equal to negative 2. That's the domain. Any asymptotes? An asymptote will be at negative 5. Since as x tends to a very small number, log 2, this entire thing will tend to, this will tend to 4. So as x tends to negative infinity, log 2 to the 4 plus 2x minus 5 will tend to log 2 to the 4, which is 2 minus 5, which is equal to negative 3. So this will tend to negative 3. And it will intercept the axes at, of course, where will this intercept the axes? Okay, 5 is equal to log 2 plus 4 plus 2x. 2 to the 532 is equal to 4 plus 2x. 2x is equal to 28. X is equal to 14. So this will intercept the axes at 14, 0. And when x equals 0, we have 4 to negative 3. Oh, sorry, no, this asymptote will actually be incorrect. Sorry, what I mean is actually negative 5 over here. So the asymptote is negative 5. We have a y-intercept at negative 3. So we have this and an x-intercept at 14. So this is 14, 0. This is 0, negative 3. And this asymptote here is y is equal to negative 5. So it should look like this. So that was all for the speedrun. I hope you enjoyed, and I hope to see you in the next one.